go. Our last topic of the year for pre-calc, the discussion of limits, your first topic that you'll find in calculus next year. Okay. Now, we've actually used this notation throughout the course when we were talking about end behavior. But now let's talk about it a little bit more definitively. Okay. Here's the limit symbol. Okay. It says the limit. It's asking you basically if you approach the value of x equal some value, some arbitrary value of c, okay, on a function, what value does the function approach? What value is the y value approaching? Again, the operative word here is approach, okay? So if there is a limit, and we call it L, then the number L is the limit of the function as x approaches c. If, as you get arbitrarily close, but not equal to c, there's a condition, okay, close but not necessarily equal, the values of the function, specifically the y values, become equal to, or at least get very, very close to, the value of L. Then we can write the limit as x approaches this value of c of the function is L. So here's our example, a general and a specific example. Okay, here's our function, all right? Here's our x value of 4. Now, as we approach means we have to approach it from either side, from values slightly larger than the x value of 4. That doesn't mean at 10 or 8 or anything. Values just very close to 4, okay, but slightly larger. And as we approach it, okay, from the left side, values slightly smaller, okay? If upon each approach from the left and the right, we're moving towards a value, a definitive value, then we can say the limit as x approaches 4 for this function will be equal to that value, in which case it's 5, okay? So that's where we write this. The limit as x approaches 4 for this function is equal to 5. Again, it says the notation indicates that the limit as x approaches c is equal to some value L. Because the limit does not depend on what happens if x is exactly equal to c, limits are useful in studying how a function behaves when it gets very close to a number at which the function may not be defined. That's a very important concept, okay? So a lot of times, all right, we're going to be asking the limit at some points that we have some interest in. Mainly some points maybe where the function's not defined, so we'll see that, okay? I said about from the left and from the right. If we're going to make a claim that the limit, sorry about that, let's go back. If we're going to make a claim that the limit as x approaches c of a function is equal to some value L, then we can only make that claim after having examined the limit, after approaching that value of c from the left side, as indicated by the minus sign up here, the raised minus sign, meaning coming in from the left, okay, and coming in from the right, values slightly larger. If upon approach to that value of c from values slightly to the left-hand limit, and values slightly to the right-hand limit, we approach the same value, then that value is equal to L. In other words, this statement here about x approaching c cannot be made until both of these conditions are satisfied, okay? All right, so here is an example from a table value, all right? So we're considering this example, the limit as x approaches 1 for x squared should be here x squared minus 1 over x minus 1. Now, obviously the function is not defined at 1 because it produces a 0 in the denominator, which is precisely why we ask for the limit. because that's what we're interested in. What is happening at that point, okay? So that's typically what's going to be asked is what's happening at these values of x where we have something happening. So here's a table value, okay? And before we examine what happens as the limit approaches 1, we're going to look at it from the left side and from the right side. So the tabular values say, okay, here we are approaching x from the left side. So values slightly smaller than 1, okay? A tenth of a unit from 1, a hundredth of a unit from 1, a thousandth of a unit from 1, okay? Likewise, we approach x on the positive side, we approach x equaling 1, okay? From values slightly larger, a tenth of a unit larger, a hundredth of a unit larger. And what we're seeing is the function values are being driven in each instance towards what appears to be 2, okay? On the left side, when we're within 100, when we're within a hundredth of a unit from 1, the function value is a hundredth of a unit from 2. This keeps happening. I'm sorry about that. When we're within a thousandth of a unit from of 1, the function value is within a thousandth of a unit of 1 on both the left and right side. Okay, so therefore we're going to say down here, since the limit as we approach -1, okay, I'm sorry, since the limit as we approach 1 from the left side, the negative side, is equal to 2, and the limit as we approach 1 from the right side, slightly larger values, okay, is equal to 2, we're concluding that the limit as we approach 1 is equal to 2. Even though the function is not defined at 1, the limit does exist, and in this case is equal to 2. So the key thing that we're trying to get to in this video is the notion of what a limit is, okay? And the limit can only be existing if, as we approach this x value c from both the left and the right side, we move towards a definitive value. In this case, our definitive value is 2, okay? And therefore, we're going to make the claim, that being said, that the limit as x approaches 1 for the function x squared minus 1 over x minus 1, the limit is 2.